Assalamu alaikum warahmatullahi wabarakatuh. Good morning to all. Today, on this occasion, we are having a special talk that will be presented by Dr. Suhail, our colleague. And before starting his talk, I would like to invite our head of the department, physics, Professor Shabir sir, to come and present his views regarding this talk. Thank you very much.
Our senior colleague, Professor Gulzar Saab, Altal Saab, and my junior colleagues and his friends. It is a matter of great honor for me that for the first time in the history of Department of Physics, we are organizing a lecture series for which my immediate student, Dr. Suhail, has volunteered to be the first speaker of this special series. Insofar as delivering the lecture on different topics is concerned, I know the gravity of this revered colleague who has inspired me even when we were together doing our research at Jamia Millia Islamia. He is having his eye not only on the subject of physics, but I'm sure that he is having the mastery in every kind of knowledge that one is associated, and he is every time, wherever I have had the interactions with him and I have seen him interacting with the rest of the persons, I have always found him involved and giving his best, and he has always motivated me to see to it that I should hear him that too with my utmost attention. So without wasting my time, I think that my words will not enthusiast you to the extent the way he would be in a position to motivate you to take those very lines which he has already taken. So with these words, I extend my hearty congratulations to our Dr. Suhail Saab for motivating us to organize such kind of programs. I am sure that such kind of activities will be organized by our departments in future, and the rest of my colleagues will also volunteer themselves for such activities. With these words, I thank you all for coming to this very place and sparing your time today. Okay, thank you.
First of all, I'm very thankful for our revered HOD sir for having a very kind introduction of me. So the topic and other colleagues also in the department. And the topic which I have chosen for this today's talk is existence of space and time. So the existence of space and time, actually I just took it, I borrowed a book from the library. It was, the author's name was, I don't remember the exact name of the author. I'll just see it to the end if I can remember. But I found the title very much inspiring. Although it may be vague also in the sense that the existence of space and time, it may has many dimensions to it. So it's not only how as a physicist would like to address this question. So from commonsensical understanding to philosophers to physicists to how even theologians have addressed this question. So it has many layers, and there are layers within the layers. And to just come out to have what is space and what is time. Because the moment we come into being, the existence, our very existence is very tied intimately to this very question: what is space means where we are, how we can perceive this world. And in that world, there is some intuitive passage in which we are moving, whether forward or there is an intuitive sense as something has passed since. And that since, we don't know. It may be when the universe started, or it may be since infinite, whatever that may be. So in common mythologies, or in common religious texts, or in common philosophies, if you, for example, I just saw two quotations which I found interesting. I just while preparing this lecture, I just circled through Mr. Thor Wheeler, a book on gravitation. So he has quoted a quote from Vyasa and Mahabharata. So he has quoted, so I will not quote the 4 sentences, but he has this sentence captures the meaning of time in that sense. Is, was, shall be, or time's children. O reasoning be witness, be stable. So what was, what is, and what is going to be. So these are 3 dimensions how we try to visualize time as such. And in the what was, what is, and what would be. So it's a conceptualization of human perception. So is it real, or is it metaphysical? To quote the things, what is going beyond physical, maybe metaphysical, or is it existential, or how do physicists try to perceive it? So again, I just will quote another physicist, Richard Feynman, famous colorful physicist Richard Feynman. So he has, if you go to his first volume, volume 1, physics. So when he comes to the description of time, so he is saying, what's time? So what he is saying about time is basically, first of all, he says, so he just quotes Weber's definition. Time is a period, but then he is himself not satisfied with the definition. If you see that sentence, he says, time is what happens when nothing else happens. Again, he feels that definition is not satisfactory. But then he says, okay, let me say that time is how long we have to wait. So again, that I found that definition to me is also not satisfactory in the sense how we can characterize time. Characterize time in the larger sense. So the pointers I would rather like to just before going into the subjectivity of time, how we can have a subjective notion of something is moving from past, present to future, and as an innate consciousness. So how physicists try to perceive not only time but space. And the question whether we can perceive space independent of time, whether the existence of time can be independent of space, or our notions, whether the special theory of relativity taught us that we have to understand, or Minkowski taught us, we have to think space-time not as separate as something called space-time. Space-time manifold, in more sophisticated language, you can say. Or is there one space, one time, or there are many space times, or there are many spaces and many times? So this is, so you can have, can existence of space be there independent of time? Can existence of time be independent of space? How we perceive space and time together, that's space-time. Can there be one space? Can there be one time? Or there can be many spaces, many times? So these are all questions we are going to address. So historically, if you see in the context of how people have, you might be knowing that there have been two schools how people try to perceive space and time. There have been absolutists and there have been relativists. There have been relativists. So absolutists had a notion that the notion of space and time is very absolute. So there is something absolute. Space and time are absolute. So the value of what a space, a quantity can have at a given point, it is that value. It cannot vary from time to time, or it cannot vary from place to place. So in this context, people from Newtonian, the whole of Newtonian mechanics has been formulated with this notion of taking time and space, and its culmination has been in late 18th century, the philosophy of Kantian philosophy of space and time, when he tried to reformulate the notions of entire physics of 300 years, when he introduced this notion that if you read Kant's critique of pure reason, he has used the words space and time are transcendental. They are a priori notions. Although that thing was somehow with the advent of relativity and with the advent of notions of special relativity, this thing was replaced. So in the same context, there have been, this is people who are absolutes, taking space and time absolute, and people who are relativists. Relativists, we can say in 20th century, there have been people like Poincare, people like Einstein. Einstein, we know the way he just articulated or formulated special relativity, it's textbook material. So the way he formulated notions of simultaneity and other things which we study, and the various, what I should say, implications which might be baffling for a beginner, which include time, dilation, length, and all the things. The essential idea is of simultaneity, or the notion of time, which I'll try to clear. So people have been Einstein, Poincare, Eddington. There have been many people, Whitehead, and if we go to our Muslim scholarship, in medieval times there have been people like Iraqi, and who had these people had also arrived at notion of this had a relative notion of space and time prior to these people, 400 years. But that was in context of a debate of Ashrite versus Mutazilite tradition. How they tried to understand the notions of time and space within the context of how the Aristotelian scholarship or Aristotelian philosophy, the cause and effect philosophy, it was somehow improvised by series of debates from Ibn Sina, Ibn Rushd. So how they perceive time. So the idea of time and space is a bit digressing, but I rather say the way in 20th, 21st century we study space and time, it is devoid of any metaphysics, or devoid of any theological or religious underpinnings. So we don't speak that way. But in medieval times, medieval scholarships, or in late medieval times, there was scope of theology, and it was somehow interlaced or intertwined together. For example, in the notions of dahr, the notions of, for example, in Islamic theology, there is something called wal in Quran also. There is wal asr. The embodiment, God is behind the embodiment of time. So there is a particular Quranic tradition, don't vilify time, because God is time. So God as an entity is someone who is creating all the things behind the things. So the time was perceived like that. So in that context, these people try to visualize time and space. So maybe the topic, if you could, I digressed a bit, but to say a bit that there have been notions of time and there have been notions of spaces which were not entirely absolute, which were relative. So what do you mean by when you say the notion of time is relative or notion of space? So how do we appreciate it? In the simplest context is how Einstein's greatest insight was how he deviated from the notion of time from Newton to Einstein. So what was the deviation? Deviation was this thing, or innovation or insight you can say, is that for each point in space there is an individual time or individual clock associated with it. So the notion of time has to be related or associated with number or a point in the coordinate where it is. and such that if two people have to agree on a certain event, there is something called a relative simultaneity should be there. For two clocks to agree, you have to have some sort of transformation equations or some sort of thing which is different from Galilean transformation. In Galilean transformation equation, you have simply, if you have reference frame, there is another reference frame, so there is a change of velocity, you can have a correlation. But when you change that notion of time, that the clock at measurement of time is independent of, it's not dependent upon it's dependent upon from where you measure. Their whole sort of things just get uncovered. This is what I have studied in the earlier classes of special theory of relativity. But there are some common questions, for example, which are these are the general scholastic debates. But the common questions is, for example, we say a common thing: time is a great healer, but space is not a great healer. So why? Or time flows, but space doesn't flow. So these questions, they are simple questions, but they don't seem to have a simple answer. If time flows, why don't we say space also flows? So we have a notion of time. Either time is there, it is something which is in the process of becoming. So there is some seriality attached to the notion of time. So in the notions of when Aristotle talk of time, he talks of circularity. You must have a cause and effect. You can reach where you started. So there is a seriality attached to time. But simultaneously, then the debate comes the way we have some topological notions of, for example, in space, we have a topological notion that you can go from this point to this point. You can traverse from this point to this point to this point. So if there is a serial time, can you jump that? Can you? So these are some conundrums or some questions which after some thought, initially they seem baffling, but after some thought, they might look more, they don't have easy answers. So this was basically, I'm just digressing a bit, so this was basically stated in Zeno's, is movement possible or not? So how if we have spaces made up of infinite points, and time is made up of infinite points, how is, so you cannot move from one point to another point. So people like Burton and Russell have addressed this question in their own way, having a one-to-one correspondence of a point with the number line, the Cantorian notion of space made of dense points, the timeline made of dense points, and there can be one-to-one map, and that makes things possible. But if you read Allama Iqbal's reconstruction, he has some different point. So maybe that's another discussion. So before I'm just so this was the historical part of the discussion. So I'm just coming to the physics part of it. How we can see things temporally as well as spatially. Temporally means how you have a notion of past, present, and future, or not past, present, and future. Usually, normally time flows like that. Or a notion of space, a notion of how we can construct a metric or a so how we can, so I quote, there's a person. So in this connection, there is another person who you might not have heard him. His name is Gunmore. He has written a very good voluminous text on this question, philosophy of space and time. So if I'm quoting him, so he says, for example, is there a possibility that when you go from past, present to future, is there a possibility of going from future, past, present to past? You might have heard questions like so like twin paradoxes, they are grandfather's paradox. So they lead to, these are questions of general relativity. So they lead to a lot of contradictions. But in principle, the temporal movement or spatial movement from past, present to future is as much possible as it is from future, present to past. So the notions of space and time, if we can address them in a way, even though those questions can in principle, even though you have always this notion that you can move from present, past, present, future. In principle, thinking that you can move from past, present to future, present to past. It's also viable notion. It's not a crane, or it's not off the cuff, I would say. Pure, what I would call meditation. So people earlier in medieval times, mystics used to address these questions in their own language. But in relativistic knowledge or in relativistic versions of how we try to appreciate space and time and how our measurements of clocks are there. Because Einstein's theory of relativity, Einstein did not, the notion of time, the question of time, what is time? It's a more subtler question. But in Einstein theory, we have how we can measure time. How we can, so if there are two clocks at two places, how we can synchronize them such that there will be no contradiction regarding a certain event. So that is the way we appreciate in Einstein theory. But in trying to understand the ontology of time, what time is in its existence. So the question of if time flows, does it flow only forwards? Will it be backwards? Will it be circular? Will it be linear? Will it be cyclical? The way in Hindu mythology, the notion of time is cyclical. So will it be non-linear? These are all sorts of open possibilities. In relativity, there can be certain contexts where the movement of time from forward to backward is forbidden, like Hawking's chronology, production conjecture. But in principle, we can think time and space can be thought like this also. And there have been people like physicists who don't find it it's equally possible. This is what he wants to say. So does that. So now I am going to give a brief overview of chronology in 20th century. There have been series of mathematicians, physicists, philosophers who have tried to address, starting from Newton, how this debate of space and time has evolved from last 50, 60 years or before that Newton. So I'll give a chronology and try to explain a bit how they meet, and there are various subtleties which are not normally there in the textbooks of relativity or whatever that is. They are the individual viewpoints of these relativists or physicists, how they view space and time, even though they are equally that much important. The debate is basically the notions of space and time. It predates our debate, because once we read theory of relativity, the special theory of relativity or general theory of relativity, we normally in textbooks we don't anchor the questions of relativity the way it has historically been constructed. There have been famous debates of Euclidean and non-Euclidean geometry, and there has been famous, I talked of this person, a German philosopher, how he formulated Newtonian mechanics, a priori notions of space and time, or notions of space-time, whether geometry is branch of physics or geometry is a priori, geometrical truths are a priori. If they are a priori, then we mean that space and time are infinite. They have started since, and they are going to continue since, ever since, with an open future, from minus infinity to plus infinity. But there have been famous debates in earlier 16th century or later 17th century, whether geometry is Euclidean or non-Euclidean. So in that, if fifth postulate of Euclid is there, if geometries are non-Euclidean and geometrical truths are not a priori, they are not a priori. So our measurement of space and time, I'm just cutting it short, but our measurement of space and time, how it is done, and how people have different, I would say, subjectivities or opinions about how to use space and time. So to begin with, I'll start with Newton, then I'll give a brief how these people appreciated space and time. So in Newtonian opinion, how did Newton see space time? So for example, Newton thought, if you read his Principia, Newton says absolute true and mathematical time of itself. And from its own nature flows equally. Without relation to anything external by another name called duration. So for Newton, what he says, absolute true mathematical time of itself from its own nature flows equally without relation to anything external. So time as a notion, it is flowing. So it will have, for example, this point in space will have it the same time as this point in space. So something flows equally. It's independent of where you are from space. So all of the universe has the same time. So it's more, if you read the debates of Newton and Leibniz, it can be compressed in this one sentence. Nature is a clock and nature has a clock. If nature has a clock, that means there's a Newtonian time. So every point in time in space they have the same time. If nature is itself a clock, this means time, the notion of time may vary from point to point. And that was more how Einstein and time we appreciate that each point in space has its own clock.
So
and rest.
I am very curious. Later I might forget it. As with the relativity start, can time stop somewhere? Just like space can stop expanding some point of time. But you are saying that this time is also like a clock. So time is dependent on space, or space is dependent on time likewise. Whatever you see.
So there are two answers to this question. So
if somehow this clock stops to move, then what about the space?
So again, I am saying that is time a property which has been created in space? So this is a question.
So how are going together now? They are going together.
So if you have a
Suppose time stops, what about the space?
so there are two questions. So in the start, I started there are many spaces, many times. There can be space and time. There is space time. There are space times. These are different possibilities. So maybe one of possibilities what you are saying is space
I
stops.
am only concerned about space and time.
Or if then there are
Two variables. Suppose dependent and independent. For example, I want to write.
No, it's not dependent. It's the way Minkowski says. Now space and time have to be thought as together.
Oh yes. So
That will
is it
cause-
possible that one stops and another keeps on running, or one
So-
both are running?
So
there are three
in Newtonian mechanics, space and times are old stages. Space and times are innate in themselves, and things are moving. It's a stage, and that stage is very inert. That is just being filled by events which follow it.
Suppose some event is happening. I have a clock with me, somehow this clock stops. I have not been able to measure that much of time, but event is going on. But I am not able to measure that. What about that very time? मैं किसी event पे जा रहा हूँ. I am performing my experiment. Whatever the clock, atomic clock, whatever clock, observational clock I have with me, somehow it stops. It's not working likewise. What I mean to say. What about that much of time? thought that when the clock is not working or was not working. आपको समझ में आ रहा है?
Clock, you have not to understand in that traditional sense that clock is just like this thing. Clock means that all the net forces in nature, whatever you are made of.
They are working.
They are working.
They are
So
working.
when you are talking
I
that,
request everyone keep the discussion session reserved
Okay.
for the last. This is a lecture, let the lecture.
huh,
We will discuss it. Please.
okay. So this is the question. So this is Newton. So this is how Newton visualized time. So now we know famously people know about Einstein, but I rather before coming to Einstein, we are going to just say people from mathematics know him appreciate better, but he had a contribution in physics also. So there is a person of the name of physics, of the name of Riemann. You might have heard. So people who are know general theory of relativity or differential geometry, they know the way we write normal Euclidean geometry, dx square is equal to dx square plus
dy square.
so in Riemannian geometry we write it as
CG.
dxi dx u dx. So we write the same space element. We don't write it this way, we write it this way. So the question is, what are the motivations of going from this to this? So this was the point. So you have to be, if you are more interested, you can read the debates of how Euclidean and non-Euclidean geometry entered into this entire picture of space and time. But to cut the story short, what Newton said, he had a definition of time, that it is equally flowing. So the first person to take this notion of time, or space rather, you can then include time, space was Riemann. So what he tried to describe metric, or this basic thing, what is the distance, how you can measure distance between 2 points. So his basic idea was a bit subtle, that distance between 2 points is not independent. It's dependent on externally who is going to measure that. So the notion of distance, which was considered absolute in Newtonian mechanics, space. So the notion of distance, for example, what you are going to measure, it is independent of from where you are measuring. So he said it in a mathematical sense, but I am saying what the implications you are following. For example, you are measuring rod, it's fine, you are measuring it's 5 meters. But if you have, the rod is made up of some material which is going to melt. If you are going to measure it from a person who is very hot, the rod will go to squeeze. It's just simple, in a common sensical way. So, but what he wanted to say, the intrinsic notion of space, although it's a construction of Newtonian mechanics or Euclidean geometry, it has to be reformulated by this notion. That whatever you measure between 2 points, so it's dependent upon external to the metric. So there's a famous theorem of Gauss, theorem of adhesion, how we can calculate. That's people who study. So, but this is the idea what I want to say. So I'll just write it. So the basic metric, what he said, the basic metric relations must be sought outside the groundwork of space. Space, colligating forces that operate on it. So it's also reminiscent of, you might have heard of something called Mach's principle. That inertia of a body is also related. So if you want to measure inertia, so the entire universe has also to do with the, if you want to measure the inertia, it's related to the inertia of a given body is related to the inertia of the entire universe. So you cannot insulate or isolate a given system, even if it's a gravitational system. So you can, so the measurement of it's in the gravitational context. So these two, so he is talking of pure space only. So this is the point which I am trying to say. So
Please repeat the point.
So the basic metric relationship between 2 points in space depend on they are external to it. The person who is going to measure them. So from this it will get clear more if when you.
Sir, 1 minute, sir. I'm not asking question. If you have these 2 points, you are measuring, sir. After interaction, what will happen to this matrix, sir?
Look, I'm saying Newtonian metric or in a post-grade approximation, nothing will happen. I'll make it one point. This will be clear here. For example, this will be more clear here. So just like we write ds square is equal to dx square plus dy square. There is another way of writing ds square. If you go to the books, it's like this. You might have seen it. How we can reparameterize coordinates in a way we can again write the coordinate systems. So how we can the equivalence which were, for example, you want to measure a rod. For example, this is 5 meters. You have already a notion of meter which is fixed there. So if 2 people will disagree on our measurement of 1 meter, you will always have some standard meter, for example, which you have kept. But this is also a prior notion that where from that meter, that standard you have made. You normally go to France. So, but that's also based on some subjectivity. What is the standard? So the notions of Euclidean geometry or notions of distance which have been there. So it's not absolute, which I mean to say. The standards, even if 2 standards or 2 measuring things have to be somehow related, they should be related by some principle. That is the way we go from Euclidean geometry to non-Euclidean geometry. And there are many consistent non-Euclidean geometries also. And there are many consistent measurements in the Euclidean geometry of how to measure distance between 2 points. The famous being that for an ant moving on a football, its circle is its straight line. So ds square, if you say that from the this principle of least action, ds square is going to its straight line is its circle, that semicircle. But for normal person, it's one straight line. So these are 2 notions of geometries which I am trying to emphasize. So the point I am trying to emphasize that there are different formulations of metric distance between 2 points, and they depend on the reference frame from which you are measuring them. How you are measuring them, which geometry you are constructing, and geometries are free constructions of human mind. The only thing is that they should be self-consistent. Given starting from a certain axioms, you should arrive at theorems, and back you should come where you started. So there is an internal rigidity and consistency with regard to geometries. So whether it's Euclidean geometry or whether it's non-Euclidean geometry, or there are different geometries, but there are different ways how we can measure distance between 2 points. In Newtonian theory, the 2 points was independent of the distance between 2 points was independent from where you measure it. But in Riemannian construction of geometry or other geometries, so it depends upon how you measure it. There can be equivalences, or there can be how we can move from one geometry to another geometry. That's also the point. That's another discussion. How we can even measure angles in one geometry? Do they lead? So these lead to other questions of how something called metricity. How we can if there are 2, the way in spatial theory related, you have measurement of rods and measurement of this thing. How we can measure a given metric in one geometry and another geometry. So if there is a free construction of geometry, so for example, if Euclidean geometry helped in Newtonian mechanics, non-Euclidean geometry helped in general relativity, explaining other phenomena. So what is the choice of given geometries for point here? So here the way they had Newtonian time, how Riemann understood, here comes point. Point here said that no, it's mere convention. It's mere a given physical phenomena. Which geometry will suit it? It's a matter of convention. Which geometrical construction will address the metricity to the physical parameters in the lab, which you are going to measure? That is our criteria of accepting or rejecting a given this construction. So in principle, constructions are not absolute; they are relative. So that's why there are absolutists, there are relativists. So in this whole school we have absolutists, so relativists, that's what we call them, relativists. Our measurement depends from which frame you try to measure things, or which geometry you are constructing to measure things, and which physical parameters which are coupled to that geometry which are helping us to measure things. So for this person, it is mere convention. So again, now I am trying to just quote 2-3 people and then stop. So there is this point here, and then there is Euclid, Eddington. Eddington, you might have heard the name of Eddington. He has written many books. He was the person who first verified a general theory of relativity experimentally in that expedition. So for Eddington, so he did not agree to the characterization of that point here, that it's mere convention that which geometry should be related with it. So for him, space is physical space, and geometry is natural geometry. And if you go to books, there are examples. For example, he is critiquing him that, for example, it's like that PV is equal to this van der Waals equation and plus A by B square and something like that, E minus B. So somebody will say that the equation is not like this. I'll change the definition of pressure rather than just introducing this correction. So this is another way of agreeing on a given experimental fact. Either you account for the variables in the experimental lab, or you change the variable in the theory, still you can explain the things. So this is one of the criticisms to this. But it has another things, those are other subtleties. So I'm just saying it, or I'm just quoting it, to see the richness of how the notions of space and time are absolute. If they are not absolute, they can be relative. Even if they are relative, then there are also subtleties in relativistic notions of space and time also. Where Poincaré thought that it's mere convention, which physical fact you are addressing, we can fine-tune geometry accordingly, Euclidean or non-Euclidean, whatever. That's warranted by the physical facts, physical parameters. But for Eddington, he thought that no, it should not be mere convention. Physical space is physical and geometry is natural geometry. So he did not like that characterization. So whatever that may be. So in the same way, there are people like Brigman. Brigman is another, he might be the person who just worked on thermodynamics. So I'll just quote 1-2 sentences. And so maybe I'll quote his one side. He is quoting Playford, who says length is relational rather than absolute. So there is lack of intrinsic metric. Lack of intrinsic metric. And there's another person, if you are interested in this question, he has a really good writing work. The aspects of philosophical aspects of space and time. How you can interpret the notions of space and time within the context of a certain epistemology. How we construct knowledge as such. And what do you mean by space-time? And just like I said, whether if space has topological properties, can time be thought as a topology? Well, time is a continuous thing. Well, we can jump from, just like in space, you can go from this point to this point. Can we jump in time line also, if time is thought as topological? So these are questions, certain questions, they don't have easy answers. And the last, I'm going to quote one of the mathematicians and philosophers of 20th century, Whitehead. So in this entire league of mathematicians, I forgot Einstein. Einstein comes in the point that he was the person whose insight was that he contextualized time within the concept of absolute space. The notion of time in the context of absolute space. It's relative. You can see Einstein in that thing. But in relativistic time, the notions of space and time can be related. So you can see there are different values in terms. So the essential point which I forgot, if you read, there's something called congruence. One has studied. This is I should have said it earlier. So in your earlier classes, when you study similar triangles, congruent triangles, so it's basic notion of congruence. How we define congruence in one geometry and congruence in another geometry. For example, if two triangles are congruent, what are the conditions? SSSE, SASE. So if there is non-Euclidean geometry, how can if a triangle is congruent here, two triangles, can they be congruent here? And how we can map one geometry from another geometry? Because ultimately we are talking about space, and we are measurements in space. We fundamentally visualize space. So when the metric relation is there, how we define congruence as such? If two lengths are equal here in this space, are they same in another constructional space or not? So this is the question. They are all adhesives. So in that concept, if I just quote Whitehead saying that if this notion of congruence, which seems to be very much not violated, it may have its meaning or measurement depending from geometry to geometry and which universe you are choosing. So this notion somehow contradicts or it somehow militates our how we appreciate time as human beings. Because as human beings we feel that time is something which is there and it should be something absolute. It has been, it is there. It should not be relative. This experience of time, if we have modified it with some Einsteinian notions of time or no relative time, and it might be useful in trying to see some lifetime of some decay particles is faster or slower. So those minute experimental measurements, if this sophisticated definition of time, which is dependent upon space, if it can explain some experimental results, but why should it somehow contradict our definite notion of time, which is innately out there? This is the view of Whitehead. And he has argued his own theory of bifurcation, how he tries to visualize space and space-time continuum related to the perception of that observer. That's another thing. So I'll just end it here, what he said. So these are all, gentlemen, we normally be in Einstein time, these are all within the relative notions of time or in space, how people can be, how these variations can be there. Variations conceptually, maybe not technically or philosophically also, you can say that how we can see it. So this is also called something called congruence group. If you see in the class, one thing which I forgot is a very interesting statement of Suhail. He's a mathematician. So I'll just read it and then read another statement, then I'll start. Set of all continuous groups in space having, for example, displacement in a bound fall in Euclidean Lobachevsky-Riemann. Each of these metrics generation is not one, but infinite infinitude of congruence class. There is not one congruence class which is consistent. You can generate infinite class congruent classes or geometries, which can be consistent with your measurements, which you are measuring. Mathematicians have constructed. And as physicists, they are only going to take those measurements which are fine-tuned to the experiments. For example, perihelion of Mercury. There is a particular another Mercury moves. In normal classical mechanics, there is some tilt in the angle. That's some, for a century it is 0.23. When you only Einstein theory explains it. Newton theory is not explaining it. So we have to go to non-Euclidean construction of geometry and then embed Einsteinian theory in non-Euclidean geometry. then explain that physical variation. There are certain physical variations which cannot be even explained by Einstein theory. You might have to take recourse to another geometry, but that should be self-consistent. That's the point. So this is what he is trying to say. So there can be infinite self-consistent geometries, congruent groups which can map. So I'll end with this quote from Whitehead, and then I'll just open the floor for scientific laws are stated relentlessly to particular congruence groups, particularly congruence groups, thus investigating. So we are investigating elliptic, hyperbolic, or parabolic, or whichever geometry you are. These are the simplest constructions of spatial. So he's again coming to the prejudice of spatial congruence group is perfectly a definite problem decided by experiments. So I'll just so he is also prejudiced. So whichever geometries we are constructing, non-Euclidean, which might have a particular map to a physical problem, so that should be decided by experiment. But in principle, in principle, you can think or you can construct spaces, times in all possible manners. And whether, why I said, why should not time flow, why space doesn't flow, or these questions, whether time flow from past, present to future, they are all equally logically possible questions. So it's which question you are trying to address. And basically how we measure space and time, in which construction. And there can be equivalence from one space-time to how we can see it. So if it's clear, I will stop.
So first of all, I apologize my colleague, Dr. Ahmad, for interrupting during the lecture. I think with the permission of HOD, I would like to, on behalf of HOD, through this session for questions.
So I have one question. It's a debate kind of thing. So when we discuss the space-time, existence of space-time, the whole structure is based on the electromagnetic theory. We use this electromagnetic equation. We have 4 electromagnetic equations, 4 Maxwell's equations. Why in science we have only 4 Maxwell's equations? Why not 3? Why not 5? Because they're philosophical.
For example, I just quoted this undergraduate question.
Can I comment to what you asked? I think there are only 2 Maxwell's equations.
No, that is
And the
actually
actually
derived. No, 1 minute. It is partial mu F mu is equal to J. If there is no source, we have homogeneous. If there is a source, then we have
Then there is
homogeneous.
only one equation.
So there's only one equation. Partial mu F mu is equal to J. If we have the current source, if there is an existence somewhere, there is no fluctuating something. So we have this inhomogeneous equation. But when there is no source, we have this homogeneous equation. But overall, we have 4 Maxwell's equations. They are the coupled equations. Because the lecture, we are discussing about philosophy of the space and time.
The existence of space.
Existence of space and time. My question is very simple, sir. Why on philosophical ground we have to make a debate? Why there are only 4 Maxwell's equations? Why not 3 or why not 5? Because you have the space curvature. Like we have 4 vector.
For example, there can be a possibility. For example, in group you see this.
No, sir. 1 minute, sir. You are discussing these, making a connection when you make a measurement in space time. You are using a metric. This is what I said, that when you make an interaction, if you have one line and another line, the two lines are interacting, okay, in space-time, because there are infinite number of spaces. The two spaces are interacting. At the point of the interaction, we are using a metric, but we do not know what is the direction of the new space there. Like this line is coming here, this line is coming here. They are interacting here. There is an interaction with metric. Now, how we can know the direction of this space is here and the direction is there?
For example,
Okay.
the metric we have, when we talk of space-time is made of space-time manifold. When we have dxi, dx mu, mu can be, we can take infinite spaces. In four-dimensional space, maybe in case of electrodynamics, there is a Closure-Klein theory, or there are various unification schemes, which was started by Einstein. How we can couple electromagnetism to this gravity, and there is an attempt by Closure-Klein. How in fifth dimension we have this EMF field, how it can be coupled to a higher dimensional theory of electrodynamics to just generate a unification. These attempts have been there. If you have, there is another relativist Herman Weyl. If you read his book Space and Time and Matter, he has also attempted unification of electromagnetic field along those lines. There is not more dimensions. There are more dimensions to not force three spaces in one dimension. So these are attempts. And to address your another question, maybe for example in group there is a particular problem. For example, if there are magnetic monopoles, for example, del dot B is equal to 0.
Yes.
If you assume that universe has a magnet, if you have, how we can modify Maxwell's equation? We can do that exercise, but since we have not seen them, it's a theoretical possibility. But conceptually, we can do these exercises.
In the Holy Quran, it says, Holy Quran, it is mentioned in the Holy Quran. Do not the unbelievers see that the heavens and the earth were joined together? At that time, we have the singularity that never not be existed. So these poles are not called Dirac poles, because Griffith discusses this issue.
I'll quote Quran in the context of how in Quran, for example, there is a verse Wal Asr, or in Quran there are verses like God is the who just comes. He is responsible for succession of events. Din ki baad raat aati hai, raat ki baad. He is behind the things. There are notions of Dahar. There is notion of Dahar in time, and there is notion of Asr. There is Dahar, and there is another called Sarmad. For example, timelessness. For example, when in common parlance in a religious literature or folklore, you can see in Quranic verse, we see of those 7 people in Ashab al-Kahf. You see that 7 people went into that cave, they lost the sense of time or sense of mirror. So this is also one possibility of realization of how time can be still. You can only have time. You lose that notion. That as an ideation you can take it. But exact relating it should be different. For that you need to have an exact what does it mean. So I am not qualified to talk about this. But this thing I can say, in general notions of time, they have been talked in all religions.
So one thing
talking about Islam,
yes.
God as a creator, he is behind the events. And I'll just add one thing. For example, the way he asked this question, the notion of time. For example, Saint Augustine said, what was God doing before when the universe created? The answer has been given by Mullah Sadra, who was a 16th century theologian. He said that the existence of time as a property has been created by God. So the question doesn't arise. If time was eternal, then the problem arose. But if it's a property which has been created by something, so it has started some point in time. So he just theologically could.
So from the existence of last two things, from the existence of space and time, when we make the major matters, can you prove that we are born before our parents?
Oh, that's what called the grandfather's paradox. So that's what I'm saying. That this person, this Brigman, so what I was talking about, topologically, if time can be topologically thought of. For example, if space is topological, means we can jump from this point to this point. But when you think of time, you think it's serially moving. But can you just jump from this point to this point? If time is topologically constructed, we can think that way also. So these are all constructions. You can go from past to future, future to past. But whether they are viable or not. For example, there are, for example, grandfather's paradox. So So there are constraints. So different relative, if you read general relativity, there are conjectures, how some people say they cannot be allowed, some say they are allowed. There is a thermodynamic notion of, so the how we see notion of time and space.
Sir, how can we
If it
define
is,
superliminal velocity?
one is retrodiction.
How we can, sir, define a superliminal velocity? Some common examples of time dose of phenomena. If we go from past to future or future to past, how we can define superliminal velocity?
No, they can be non-local events in space and time. They can be non-local events, but as of now we have not an experimental this thing.
Suhail sir, you said that there is this Newtonian and Kantian philosophy. They are actually same.
But they are not saying, I'm
They
saying,
are based on Newtonian mechanics.
no, actually I'm saying the point of Newton that time is something, it flows equally at all. So it was taken by
Nature
Quant.
is a clock, that's what you said.
Clock is a nature.
No, there are two questions. Nature is a clock or nature has a clock.
That's not my question actually. I want to start from here. You said that Newtonian and Kantian times are something what you can classify in absoluteness of time, right?
And Kant used the notion of space and time as a priori. A priori means they have been there.
Exactly.
So he just basically, what I could say, he summarized the 300 years of.
Whether they are mingled together or they are not mingled together is a different thing. Then you said that there are many times in this context. You can construct many times. You can construct linear, non-linear, circular times. When you say that, see.
So the way there is something called metric, I talked of metric congruence. I talked of
My question is when time is absolute.
in Newtonian context.
In Newtonian concept, you said that when time is absolute, you do not have another quantity to compare it with. You can compare an apple with an apple.
This I was saying before medieval mystics thought like time like that, and Hindu philosophers had thought.
My question
So people had realizations of time. Time can be thought this way also. It was Newton only who said that you should think time only this way, and it was successful for 300 years.
My question is, in the Newton, this is what I think about it. When you say Newtonian, in this context, in Newtonian concept, or this Kantian context, we have a choice of constructing time in whatever way we can, because we don't have a comparison of time with anything.
It is given. It is pre-given.
In Einstein time, we are bound because it is something relative. But in this Newtonian time, we are free to choose.
In Newton time, we are bound.
Like we are free to choose the scale of anything. We can scale it by anything.
In Newtonian physics, we are fixed. In Einsteinian time and space, we have freedom.
Freedom of moving from one
And the way we have, for example, space congruence, we have time congruence also. The notion of time, this is a subtle idea. This is what you have to think over it. The way we thought of space cannot be congruent. The measurement of in the same way, time is not necessarily congruent.
I'm not going
between
there.
two.
This geometry follows from actually when you project relativistic, special relativistic, Minkowski geometry to general relativity. Because the results are geometric, it's obvious to project it from or to think it from geometrical perspective. Now the problem is in this Newtonian case. See, you are saying that we can have many times.
No, I'm not saying Newtonian. I'm saying mystics have previous thought. Newton's point was cut.
When we say that in the
It's not Newton. It's not. I'm saying that before Newton, for people thought.
Okay, what makes you say
Newton made us to think time can only be thought this
what
way.
makes you say that there are many times? There can be many times. Is this, first of all, you categorize this question in absolute or
So it
relative?
comes from this, which I have said, na? The congruence. There can be freedom to it.
Since you said it at the very early
I'm saying in principle you can construct it that way. In principle you can construct a congruence group, metric, one sort of metric, another geometry, another metric. In the same way you have one sort of time clock in one this geometry and another time clock in another geometry.
Okay, let
So
me
you can
come-
construct universe accordingly.
Let me come to
So there is a notion of space-time. So if you have one space and one time, but you have another notion of time, which may not be linear or non-linear or
So
circular,
you also
and you can conject it with this space, and you can construct another universe.
you
So there is a
also
lot of freedom
you
of
also
constructing universes also.
point here that there is that conventional geometry.
No, he said that he was more convenient. He said it's whichever is convenient on ground for a physicist. The
We have to
geometry.
choose it.
Huh.
We have to choose. As
So there
per-
is no intrinsic truth value to
We
the
can
theory.
choose a short shield metric, we can choose a curve metric, Disitter metric, whatever is.
No, no, the geometry in which that is formulated.
This is what I mean by choosing a metric.
No, no, choose a geometry, you choose a solution
By
of curve
choosing
metric in a
geometry.
Euclidean geometry or
By choosing a geometry and by choosing a metric. Is this correct? Point here said choose a convenient metric. I understand.
choose a convenient metric to explain physical phenomena.
I understand choose a convenient metric.
No, not convenient.
I take it as, yeah, you said it. You said choose a convenient. No, you said convenient geometry. I know it. But I take it that there should be further more. It should be take a convenient metric. Right? Do you agree? Or slightly maybe it's a point
No,
of
that
order.
as a
Then
freedom
there
would
comes-
use when we
there
just have
comes-
exact solutions of
I am not tracking you in anything, but then there is this big man. He says there is lack of intrinsic metric. And he comes right after that Eddington comes.
So these are different reformulations how people have understood how do we understand space and time are relative. How these different physicists and mathematicians or relatives try to understand space, and if they understand space and time are relative, what are the different implications? And within those implications, two mathematicians or two physicists may disagree on a subtler point. We may have a certain implication by which he will explain something, but from the same implication, something gets unexplained. And some person will have another implication, so that's it.
Okay, let us discuss this Poincare's point. Choose a convenient geometry. What makes us choose a certain specific unit sphere metric with negative curvature for as a metric of universe? Why not a positive curvature?
So this is a question people are having the solution. For example,
Because
when you have Einsteinian
when we give, no, my question is
constant
going from
Einsteinian
geometry
geometry, when you have Einsteinian equation or mu, left hand side we have a cosmological constant. So that's
So
one
we
the
have
value
reason.
of constant can be minus or
we
it
have
can
a
be plus.
reason for
So when you map in a hyperbolic geometry, the geometry accordingly adjusts to the value of plus minus.
That is
If
what
it is
mean.
positively curved or it's
So
negatively curved, it's
choosing a
accordingly.
metric means actually choosing a geometry.
Huh.
That's my point actually.
So, but I was basically anchoring your question in the larger questions of Euclidean and non-Euclidean geometry. So you are talking in non-Euclidean geometry how we can see black holes.
So it does not this metric actually it makes us to if you have two geometries like your linear
Today I
geometry
was
and
reading
non-linear
a
geometry.
statement by this Whitehead. He was saying,
No, I am not stating about statements. I am saying, sir, if we go to the PG students to teach these things, this metric does it mean that if you have a linear geometry, like Maxwell's equation, you have a linear equation. If you want to go into the non-linear space, non-linear geometry, when you make a mapping from the linear to the non-linear mapping, is this metric helps us in this?
so that's what I was saying. Close applying this.
It helps us in making this
There are
transformation.
problems of electrodynamics like closer Klein formulation of electrodynamics you should see. Or Hermann Wheel has seen it, how he compactifies fifth dimension. He has tried to attempt unification problem by this, using these things. People are attempting. The problem is that we don't, in our classes, study Euclidean geometry. First, we should also have course on non-Euclidean geometry. And then how physics is related with geometries. Then, and also part bit of philosophy. Philosophy, how physics is experimental or theoretical. Then we can properly contextualize it.
I do have the courage of asking one simple question, but I want to answer in this simplest way. We are saying that the times are different. Now, could you please throw light on this video point as to how we can think of that the time can be circular?
You can start some point and you reach where you started. From this, actually, you have a notion, for example, how philosophers, if you read Involve, if you read lot of, they take, when you take time is relative or absolute. So the notion of time can also be something how subject to it. How do you measure time? With emotion, how do you see time as a subjective process also. So the way I said, then space flows wider, time flows wider than space flows. So these are questions.
So in space rotation, if you have some kind of a space rotation.
So ontology of space is basically to use the being. The notion is proper word is ontology or being. So our appreciation of time. So how do we appreciate it? Is it somehow related with my emotions, my life, how I see world? So people normally physicists have physical aspect. They take physicality. They are maybe more. So that's what I am saying, that how medieval mystics, philosophers address the notion of time and space. It's different how after 20th century people bifurcated these subjective elements from how we see. The observer is very cold. Even though in quantum mechanical observer has some perturbation to system while he is measuring it. But in principle we feel that the observer is very cold, he is emotionless. So there also we have this notion that time, or how we appreciate of time, it is devoid of our personal subjectivities or emotions. So this is an attitude.
These physicists use this circular times or different times in their models or ideas.
Yes.
They use it.
There are solutions. General relativity, it's all game of constructing a metric.
So is that
There are Godel-like solutions. There are so many. There are a lot of. But the only thing which I said in mathematics or in geometry, the constructions should be consistent, self-consistent. For example, if you start from A, you go to B, and you go to C. From C, you should come back to B. It's that it should not lead to contradictions. It should be a self-consistent, rigid framework. Just like in a cricket game, you start. Rules are there, but once you play rules, you should not violate these rules.
That's like a partial mu, J mu equal to 0, the continuity equation. You have a system, a rotating system, X, Y, and Z. You are rotating the system. X goes to X prime, Y goes to Y prime, Z goes to Z prime. So this rotation, now you have R theta e to power minus I alpha, you I beta, I gamma. You are rotating this system. So the rotation comes in this way that again you have reached X to X prime, Y to Y prime, J to J prime. Means they coincide again after 180 degree or so. What is the rotation of pi? They again reach it. So this equation, T goes to T prime. This equation, because now there is time also, this T goes to T prime. This equation, partially J mu nu, it reaches to, you will use some transfer like a gauge there. It reaches back to this transformation. Your J prime is now reaching to J. Now J mu prime reaching to J mu. And this, because this is a partial differentiation, they reach again to back to same point. This is, I think Sir is saying that this was called circular time, like that. Where you are rotating system, you are getting back this continuity.
No, it's simple. I was talking conceptually. There is a possibility of thinking. What I was basically talking of congruence space.
Kawasaki was giving a physical model.
But that's in a particular Euclidean context. Within a context, that is fine. I am talking fundamentally the way you construct length, the distance between two in one frame. If it's dependent upon the observer externally who is observing the length. In another geometry, that length may be different. In the same way, how you construct that unit of time, the basic duration. There is also freedom to that. How you measure the interval between the 2 points. Is it standard or non-standard? If it is non-standard in case of relativity, even that measurement of that interval, it can vary from construction to construction. Then there are various subtleties.
Sir, you say that Einstein was of the view that something in equivalentability. Sir, that is the space-time, it contracts or it expands. How far we can expand it or how far we can contract it? Space-time.
how far we can. So these are.
expand or
For
there are
example-
various factors that
So
depend
these are
upon.
basically, for example, when we solve Einstein equation, there is, for example, k is equal to 1, k is equal to -1, or k is equal to 0.
Yes, sir.
We have a flat metric, we have a positively curved metric. we
Yeah,
have-
as the surface
negative.
that
So if
we have
it's-
slopes of
So it
negative.
depends upon other factors like what is the mass of the universe, what is the rate of expansion, if it's going to contract, or if it's going to contract and then come and back again oscillate.
Yes, sir.
So these are all open possibilities, contingent on the fact we don't know exact amount of matter in the universe.
Sir, I know that
Normally in physics language or mathematics language, we say in Einstein we say universe is finite but unbounded. You have heard this statement. Universe can be finite but it is unbounded. So these are different solutions.
I have just, mathematically this is a Cauchy system, right? Not a Dirichlet.
I would just say they are geometrical systems by which you can imagine how the universe can be how universe evolves. Just like
I have a linear question.
No, they were all
It is
linear.
very mathematics. It is very complicated.
No, I talk ideas.
So we
also.
have different definition of time. Okay. For example, I want is the definition of time same for this chair? Is the definition of time same for the tree? Is there definition of time same for me? That's how I am measuring the time. Or in other words, we have two persons. We have two bodies. One moving.
In Newton, you have to say that was
Then you shift it from whether it's absolute or relative. Then it is
in relativistic time also there is one thing. First is Newtonian time, the time is same. But then in relativistic time depends upon where you measure, from where you measure time. And within relativists also, the notions of how you measure space and time, how you construct a metric, that depends upon from where you are going to measure that metric and measure the time duration. There is also that freedom. And how you measure that time duration and how you measure that this metric, the distance between 2 points, there comes lot of possibilities of this.
So, sir,
There is
one
one
possibility
relative
here. So, the metric which we are considering will be quite different from the metric which the creator of that is.
Creator, you have jumped to creator. Creator means a being.
Huh? There will be
Creator,
difference because God says the time from your perspective is 1,000 or
Actually, I am the time. God,
you
I am the time.
That's why I'm talking. These examples have been there. For example, in Miraj, you have been, for example, in Islamic context, I talked of something called Asr,
Yeah.
Dahar. Dahar means duration. And there is something called Sarmad. Sarmad, it's people from Aristotle and Ibn Sina, maybe he has constructed it. Sarmad means a person, one is a normal observer. The another is perceptible observer, observing something, sensory observer, observing something, an event happening. The other is that you become, which is something called, you lose that sense of time. You become one with infinite. The way you see in Miraj or you see in Hindu mythology, something. You lose notion of time. That's there. So these are all possibilities, open possibilities. As theologians or religious people can appropriate it accordingly, but there can be people, relativists, who do not ascribe to religion. They may use words like ontology, being. So
Really?
So they give properties of universe, properties of God. You appreciate God as monistic religion. God is something which is outside the universe, outside space and time. The way Augustine constructed it, the way Gaza, so he is outside the universe.
He is outside.
It has been very nice to have many approaches of this space and time, which were not known to me before attending this lecture. Let me be honest. But somewhere I have read space on its own and time on
It's the
its own
statement of
does not
Zeno's.
have existence.
Now, from now on, they should be held
They
together.
have now got married when Einstein
Yes.
No, it's a statement.
That was the basic question.
That was a statement
Whether
of
they are
Minkowski.
independent or independent.
It's a statement of
Some
Minkowski.
kind of space or-
Whosoever has given this statement, I would like you to deliberate on this statement. Why we need to consider space and time
As a
Dependent or
the-
independent?
That's what
Yeah.
I'm saying. That your measurement, for example, in Newtonian time, time flows equally in all quantities at all times. Same. When you go to Einstein time, you say my measurement of time depends upon where point my coordinate system. Where, if I measure time this clock, I'm going to measure event this point from this. The other person is going to measure the same event this. So he will measure it. We will not agree. Because I have my location in space. That's what is called, something Einstein called metric simultaneity. So if two reference frame have to not lead to contradictions, they have to agree to on some event such that they should not. So we have to modify our laws. Those are known as Lorentz transform.
Yes.
Otherwise, we will lead to contradiction. So for two reference frames to measure, have a common measurement such that they should not, so we should know that's called metric simultaneity. We should have a simultaneous, either the two, if for example I am measuring, the distance from the 2 points should be same. That should be the case. Otherwise it will lead to problems. But today I was more subtler than that thing. That's the common in special field.
Practical example is that of neon.
Yeah.
That's the practical example. So that's why we need to marry them together.
Thank you, Dr. Saab. Now I would like to invite Gulzar sir for the concluding session. Thank you.
So, first of all, Assalamu alaikum to all of you. I must personally thank Dr. Suhail Saab for giving such a wonderful talk. In fact, it was enlightening for us to hear this thing. Personally, I am speaking that it was more technical for me. Still, I must be thankful that you have volunteered yourself. I think since the inception of Cluster University in 2017, we were supposed to conduct such type of lectures, talks, seminars. And it is mostly useful for our PG students. Now that Suhail Saab has volunteered himself in the initial stage, I hope other people will come forward. And in fact, it is mandatory for weak people also, because we have to submit our MPR as their monthly progress reports. At the same time, it is useful for students also. So I think that will be in our routine now. And I hope other people will come forward. We have done exceptional research, like Suhail Saab. So we will also get benefited and we will learn a lot. So thank you. Thank you for sparing your time. I think it was very difficult to digest this. Still we managed it here. So thank you all.